Common activation functions. Sigmoid functions we already have seen in the last video. For remember purpose, g of z equal to 1 divided by 1 plus e power minus z. G of z. This one g of z. G inverse g of z into 1 minus g of z. We see this g of z, we are going to multiply with this 1 minus g of z. Then we got this. We got this. Then hyperbolic tangent. Sorry, TF dot math dot sigmoid of z. For this function, all activation functions are linear. These all are non-linear. Sorry, non-linear. This one code flag, TF, TensorFlow code flag. Hyperbolic g of z equal to e of e power z minus e power minus z divided by e power z plus e power minus z. G of z is same like sigmoid function. E power z, this one, a scale minus pi to plus pi, minus 1 to plus 1. Here 0 to 1 in y-axis, minus pi to pi. Okay, fine. Here z minus e of z divided by z plus r e power minus x. Above to be subtract, below we have to be add. Numerator subtract, denominator to be add. G dash z, that is we can say differentiate 1 minus g of z square. We have to minus g of z whole square here. G dash of 1 minus g of z square. Okay. Then rectified linear unit. The short abbreviated ReLU. Re means rectified. Linear unit means LU. Rectified linear unit. Linear unit rectified. G of z equal to maximum of 0 comma z. This is 0. So this one. Sorry, straight line. Drain part. Sorry. Then after differentiate g of z, we got one if condition, with condition z is greater than 0, otherwise 0, otherwise 0. G z is greater than 0, then 1. Yes, 1. Otherwise 0. So here take TensorFlow TF dot NN dot ReLU TF neural network. Here math function, here neural network applying RLU, rectified linear unit. Here, all activation functions are non-linear. Okay, fine. Importance of activation functions. Importance of activation function. Activation function we have seen sigmoid function, hyperbolic tangent, rectified linear unit, RELU. Rectified linear unit. These all are activation functions. Are these all activation functions are non-linear, non-linearly. Okay. So code also we have. Okay. Importance of activation functions. The purpose of activation functions is to introduce non-linearities into the network. The purpose of activation function is to introduce non-linearities, non-linearities into the network. This is a very important point. What we are going to introduce non-linearity, where in active function, this is the very important non-linearity. This is very important. The purpose of activation function is to introduce non-linearities into network. What if we wanted to build a neural network to distinguish green versus red points? This is red points. This is green. So we have to build a neural network to distinguish green versus red point. Importance of activation function under the purpose of activation function is introduce non-linearities into the network. This is from point 4. This is non-linearity. Linear activation function produce linear decision. Linear activation function produce linear decisions no matter the network size. Linear activate functions produce this is linear activation function produce linear decision no matter in the network size. Here this is the very important part. No matter. They are producing linear decisions. In this linear activation functions, linear decisions no matter the network size. Importance of activation function. The purpose of activation function says so linear activation functions produce linear decision no matter the network size. Okay. Then what we will do? Non-linearity. So linear, this one to be leaving. Non-linearities allow us to approximate arbitrarily complex functions. This is very important. Please listen carefully. Non-linearities allow us to approximate arbitrary complex functions. This is here in green only focusing. Okay, like this. So for this focusing, what is called non-linearity? Allow what this is allow arbitrary complex functions. This complex function here. Put this way. This is complex function. Yeah. Arbitrary complex function. Allow non-linearity allows non-linearity only allow as approximate ordinary complex function. Approximate arbitrary complex function. Sorry, not ordinary. Approximate arbitrarily complex function. The perceptron example. One x1 x2. This is 1 means bias here, bias. Okay, bias. Okay, bias 1. This is weight W. So input we know already. This is W weightage. We have W naught equal to 1. W naught equal to 1. And W equal to 3 minus 2. W naught this one W, this is 3 minus 2. It is coming under column matrix. Column matrix. Okay. Y cap output. Y cap equal to G of, this is G. Okay. This is G. Yes, G. G already we have seen, huh? What mentioned? That was non-linear. Sigma function, like that, same function. This one. Now can it know? This one. Sigmoid function. Sigmoid function. Sigmoid function. Okay. W naught. This bias. X of x power t. This is transpose x power t. W over this is, okay, equal to G 1 W naught here 1, so 1 X transpose X1 X2 X1 X2, so X1 X2 transpose X equal to W equal to 3 minus 2. Now we got to simplify. Y cap G 1 plus, what is this, X1 X2, what here X 3, no sorry, you have to multiply, cross multiply. X1 3x1 is like this, row column. X1 3x1, okay, here corresponding 2x2 minus 2x2. This is just a line in 2-dimension, okay, 2-dimensional line. Right. 2-dimensional line. So Y cap, so final that answer C of 1 plus 3x1 minus 2x2. Here this is x-axis, x1 x2 x1 x2, okay. This one 1 plus 3x1 2x2 coming this way, okay. Minus 2x2